Denial of service attacks happen when a given resource, such as, let's say, a web server on the internet, is bombarded with bogus requests to the point where it becomes so saturated that it cannot respond to legitimate queries. So, for example, that web server, let's say, might be connected to the internet. We can draw the internet as a cloud. It might be connected to the internet via a router, and that router may only have, let's say, a 10 gigabit per second port. So imagine you have a router that has a port that can handle 10 gigabits per second of traffic. Okay, if in this situation somebody sent a continuous stream of traffic to that web server at a rate that exceeded 10 gigabits per second, then what would happen is that the server's available bandwidth would be used up dealing with this one source of traffic, and as a result, the web server would not be able to, let's say, have anything left, any reserves left for being able to handle legitimate queries because it is being saturated by this bogus traffic. Okay, the most straightforward way to mount such a denial of service attack is by having the attacker control a large number of systems on the internet, and then having those systems basically pummel the target system with traffic. Okay, and typically in these cases, these systems that are doing this pummeling, these systems are usually part of a botnet. Okay, they're being controlled by the attacker as part of a botnet. Okay, now that's one way to mount such an attack. It's not a cheap way because you have to have access to all these bot-infected hosts when you mount the attack. It turns out, however, that there are some attackers who have come up with more enterprising ways of being able to mount denial of service attacks in a way that requires fewer resources to mount. Okay, and they can accomplish that aim via a very general purpose concept that we call amplification. Okay, the idea behind amplification is that the attackers find ways where a small amount of work on their part can be amplified into a large amount of work on the part of the target. Okay, so the impact of a small amount of work is amplified in that sense. Okay, and one of the ways in which we can mount an amplification attack, or in a way that an attacker can mount such an attack, is via being able to find on the internet somewhere a special kind of a domain name system server. So a DNS server, okay, a DNS server on the internet that has a specific property that I'm going to go into. Okay, and what attackers are going to basically try to do is find a DNS server that's misconfigured or configured, depending on how you want to view things. Maybe it's just set up, rather, to accept incoming queries from literally any system on the internet. Okay. Now, if you have such a DNS server that's set up to accept queries from anybody on the internet, that type of DNS server is typically known in the technology parlance as an open resolver. Okay, an open resolver. And it's called an open resolver for the following reasons. It's open in the sense of being able to, or really having the approach of openly responding to any query. Okay, these DNS servers respond to a query from any user anywhere in the world, and they resolve those queries. Okay, now in contrast, if you had a more safe DNS server, a better way to configure it, a more safe practice would be to set up your DNS server so they can only respond to queries from very specific hosts. So for example, if the DNS server, let's say, is being used in an enterprise setting, then it might make sense to configure it so that it only accepts and resolves queries from systems whose IP addresses are in the range associated with that enterprise or that organization, rather than really just allowing queries from anybody under the sun. Hopefully that makes some sense. And maybe I should take a brief moment, a brief segue to explain what I mean by resolve. So a DNS server is essentially like a phone book for the internet. It can translate a domain name, like let's say sourcefire.com, into an internet protocol or IP address. And with that IP address in hand, traffic from one source host can then be correctly routed to its intended destination over the internet. Okay, so that's DNS 101, and you can learn more about DNS through other resources. But getting back into this particular video, denial of service attacks that use open resolvers for amplification basically work as follows. What the attacker is going to basically do is he's going to craft a DNS query, okay, a DNS query, and a very specific kind of DNS query to this open resolver, this open DNS server on the internet. Okay, and this query is going to be designed. It's actually going to be relatively small. Let's say it's going to be in the tens of bytes. Okay, so imagine his query is in the tens of bytes in length. Now he's going to design this query so that it has a large response. Okay, and the reason for that is that he can design a query so that he can request. Let's say, for example, imagine he writes a query that requests all the DNS records associated with a particular zone. Okay, and the zone file itself could then be quite large. For example, in addition to containing, let's say, information about a particular name server, it might also contain information about a backup name server, or it might contain information about a mail server, or it could contain information about aliases. Okay, and so you can see already quite a long list. There's also information about IPv4 addresses and IPv6 addresses, and information about DNS sec keys, and so on and so forth. And so you can quickly start to see that a single request might elicit a very, very healthy or very lengthy response if that request is appropriately crafted. And it turns out that with the right query in place, the response, all this information that's going to be contained in this zone file, can literally take up not just tens of bytes, but can literally take up potentially thousands of bytes. Okay, so it's going to be much bigger than the initial request. Okay, and in fact, if you kind of work out the math, what will typically happen is that the request size will be anywhere from, depending on how this is done, maybe 30 to 50 to perhaps even 100 times bigger than the size of the initial request. Okay, so it's quite a large factor. In fact, there's a sizable gap between the query size and the response size, and this is really why we use the nomenclature of amplification to describe what's going on here. The tens of bytes have now been amplified into thousands of bytes. Okay, now that's kind of the first aspect of this attack. To translate this amplification concept into an actual denial of service attack, the attacker is basically going to do the following. He's going to basically spoof. He's going to spoof or forge the IP address in the packet that he sends out. So for example, when he has a DNS query, it turns out that a DNS query is typically going to be sent to a DNS server over a protocol known as UDP. Okay, and somewhere in this protocol, in one of these packets, you have to send the IP address, the Internet Protocol address that you're sending this data from. So typically, in a legitimate use case, this would be the IP address, let's say, of the origin. So for example, let's say this guy is located at the address, I don't know, 1.3.5.7. That would be the IP address that would be included inside of this UDP packet in a legitimate case. However, what the attacker is going to do is, instead of sending a legitimate IP address, he's going to instead send the IP address that corresponds to the target. He's going to find out what this guy's IP address is. So maybe this guy's an IP address of 2.4.6.8, and the attacker is basically going to spoof the IP address in this packet, and he's going to say he's going to write the address 2.4.6.8 in here. Okay, and the reason he can do this is it turns out that DNS requests, as I mentioned earlier, are sent over a protocol known as UDP, or the User Datagram Protocol, and messages in this protocol really just go in one direction. So there is no kind of back and forth handshake as you might see with a protocol like TCP, for example. And because there's no back and forth handshake, there's no opportunity for the DNS server to really know if it's talking to the right person. It never has a chance to ascertain that information. And so as a result, the attacker can simply modify the source address, and the DNS server will think that the packet was received from the victim. So instead of actually responding to the attacker, all this traffic is going to be sent to the victim instead. It's going to be sent to 2.4.6.8 instead of being sent to 1.3.5.7, simply because the DNS server thinks that it's 2.4.6.8 that was actually sending the initial request. Okay, now to make matters worse, to really exacerbate the situation, when a packet of data is too large, it can exceed what's known as the path maximum maximum transmission unit, or the path MTU. Okay, and when you exceed the path MTU, your data packets get fragmented, and they'll get fragmented into a bunch of smaller packets. Okay, and so imagine that they're going to get fragmented instead of this one big packet. The packets will get fragmented into a bunch of smaller packets, and these smaller packets will then all be sent eventually to the target web server, and the target web server then has to take all these smaller packets and reassemble them into a single larger packet. So then it just adds to the complexity that is executed on behalf of the target server. The amount of work the target server does is just increased that much more when you factor in the cost of reassembling packets. And so maybe one quick physical analogy might be appropriate. It's like, imagine you were playing a prank on someone by, let's say, calling up a pizza delivery place, making a large order, and then giving them the address of the person on whom you're actually playing the prank. Now, if the pizza place doesn't really verify the authenticity of the caller or employ any other security measures, like, let's say, taking a credit card number, then the victim will receive an unexpected and a large number of pizzas delivered to their house. Okay? Amplification attacks via DNS resolvers work on this same principle. A small initial request is used to generate a very extensive response. And by providing a fake IP address, this extensive response gets sent to the target rather than being sent back to the real origin, which was the attacker. Okay? And then by repeating this process, by making repeated requests, the attacker can quickly saturate the available bandwidth of a particular web server and thereby cause that server to deny service in response to a subsequent legitimate request.